One of the very basic concepts in linear algebra is a concept of a point or a vector. So let me explain it to you with simple coordinate geometry that you might have learned in your 10th grade or even in your 11th or 12th grades. So let's assume I have a coordinate system like this. Let's assume this is my x-axis and this is my y-axis, right? Just for generality, what I'll say is instead of saying x-axis and y-axis, I'll call this x1 axis and I'll call this x2 axis from going forward, from now on, right? Because the problem is if I have 5 axes, what will I name them? X, Y, Z, W, K. So I would rather say x1, x2, x3, x4, x5, right? So let's assume these are my 2 axes, and if I have a point here, right? Geometrically speaking, this is a 2D surface. This is a 2D coordinate system. Let's assume I have a point P here. How do I represent this point? I represent this point with two values. The first value corresponding to how far away is this point. So I basically draw these 2 points. So this point is, let's say, 2 units away from my origin. This is my origin. Origin is basically 0, 0, where your x-axis, x1 axis value is 0 and x2 axis value is 0. So here I would say this point has my x coordinate as 2 and my y coordinate could be 3, right? So this is how I represent a point. I represent a point basically using a vector. So I can write my P to be a two-dimensional vector, right? This is a two-dimensional vector, right? So I write my P to be a two-dimensional vector with components 2 and 3. Just note the terminology that I'm using. This is called the component of a vector. This is called the x1 component. And this is called the x2 component of your vector. Now, what if I want to represent a point in three-dimensional space? For example, I have 3D space like this, right? I have x1 axis, I have x2 axis, and I have x3 axis. Suppose there is a point here, right? This point Q now can be represented using a vector of size 3. Let's assume it is 2 units away from x1, 3 units away from x2, and let's say 5 units away. Then I can represent my Q with a vector of size 3, right? So a three-dimensional point can be represented with a vector of size 3, with each component corresponding to how far away is its origin on that component, right? Now the immediate question that I get is, how do this is a two-dimensional point and this is a three-dimensional point. Okay, it's a three-dimensional point. What about an n-dimensional point? How do I represent an n-dimensional point? Because I promised you that linear algebra is all about taking our learnings from 2D and 3D and extending it to n-dimensional spaces, right? So given any point, suppose if I have a point x, I can represent it in n dimensions with n components, right? I could have 2, 3, 4, 1, 5, so on and so forth. If I have n values, here, it will represent an n-dimensional point in an n-dimensional space. So this is a two-dimensional space. This is a 2D space, right? This is a 3D space. Of course, all three of them are perpendicular. Of course, we can't visualize a 4D space or a 5D space, but mathematically, I can write a point in n-dimensional space by using n components here, right? So this is very simple. This is a very simple idea of what a point is. Now, the next immediate question here is, what's the distance of a point from origin, right? So what is the distance of a point? Distance of a point from origin. We learned all these simple ideas in coordinate geometry, probably in your high school, right? So let's take 2D, right? We'll always learn a concept in 2D and 3D and extend it to high dimensional space. Let's assume I have 2 dimensions, x1, x2. Imagine if I have a point here, right, with components a and b. What does that mean? That means that this length is a and this length is b, right? Now what is a distance? So, and this is the origin, right? This is my origin. So what is this length? This is nothing but the length of, or the distance. This distance d is nothing but distance between origin, right, and point P, right? This distance. And what will that distance be? If you just simply apply Pythagoras theorem, this length is B, right? This length is A. So what is D? D is nothing but A square plus B square under root. Simple Pythagoras theorem, right? This comes by just applying your simple Pythagoras theorem. Okay, this is in 2D. What about 3D? In 3D, I can have the same argument. Suppose if I have x1, x2, and x3, and if I have a point here, right? If I have a point P, which has three components, A, B, C, right? Again, by simply using Pythagoras theorem, I can prove that the distance of this point from origin, let's call this D, the distance of this point here, in this case, is nothing but, okay, let's call this P dash and D dash, just for simplicity. Your D dash is nothing but A square plus B square plus C square. Again, this you can prove very simply, very easily using Pythagoras theorem multiple times, right? Now my immediate question is, this is what it is in 2D, right? This is what it is in 3D. What about ND? If I have an n-dimensional point, right, what is the distance of that point from origin? The distance is nothing but, so let's assume I have an n-dimensional point with A1 as the distance from as a first component. So I'll take A1 square, A2 square, so on and so forth, AN square. If my point P is A1, A2, A3, so on and so forth, AN, right? If my point P has components A1, A2, A3, AN, then the distance of this point from origin is nothing but A1 square plus A2 square, so on and so forth, AN square under root. So what we've learned in 2D and 3D, we can easily extend it to n-dimensional space, right? As I promised you, this is what linear algebra provides you as a basic tool. Now, next important concept that we'll see is distance between 2 points, right? Distance between 2 points. So let's say, again, let's learn it in 2D first. Then we'll extend it to 3D and then to n-dimensional spaces, right? So let's assume I have two axes x1 and x2, and I have 2 points P and Q, right? Let's assume P has A1 and A2, and Q has B1 and B2 as the respective components. Now I want to find the distance between these 2 points, right? I want to find this D, and I can find that D. If you remember your basic coordinate geometry, this D is nothing but A1 minus B1 square plus A2 minus B2 square under root. Again, this you can easily prove using Pythagoras theorem. Let me show you how, right? So what is this distance? This distance is nothing but this distance plus this distance square, right? If this is perpendicular. And what is this distance? This distance is nothing but, on x-axis you have B1 as this point, you have A1. This distance is nothing but B1 minus A1. Sorry, I should have, yeah, it's basically same. B1 minus A1 square, or A1 minus B1 square is just one and the same. Now this is nothing but A2 minus B2. This height, right? Now your distance between these 2 points is nothing but A1 minus B1 square plus A2 minus B2 square, right? Similar thing in 3D, if you have 2 points P, which is A1, A2, A3, and you have point Q, which is B1, B2, and B3. The distance between P and Q, right? The distance between P and Q, if it is D, I can write it simply as square root of A1 minus B1 square plus A2 minus B2 square plus A3 minus B3 square. Just under root of all of that, right? This again you can prove using basic Pythagoras theorem by applying it multiple times. Similarly, in ND space, if you have 2 points P and Q, such that point P is A1, A2, so on and so forth, AN, and point Q is B1, B2, so on, BN, we can write the distance between P and Q. The distance between P and Q can be written as square root of AI minus BI square, right, and I'll summate this from I equals to 1 to n. I've just written it in more concise form. Basically, I'm taking each a1 minus b1, squaring it, plus a2 minus b2 square, and I'm, instead of writing it in this expanded form, I've just written it with a summation notation, right? So this is nothing but square root of this. So again, distance between 2 points, same idea that we learned in 2D and 3D, we're extending it to ND. Throughout linear algebra, when we learn our basics of linear algebra, this is what we'll do. We will learn a concept in 2D and 3D and extend it to higher dimension. Let's learn some simple terminology and notation here. So we have two concepts. One is called a row vector. The other is called a column vector. A column vector. Suppose if I write my vector as a row, where I have elements, let's say I have a vector A, and I write it as A1, A2, A3, so on and so forth. And let's assume it is a vector which has n components, right? Then when we write it like this, it basically has one row and n columns, right? First column, second column, third column, so on and so forth, nth column. So when we have something like this, we write as a subscript, we write it as 1 into n. This represents the number of rows and this represents the number of columns. Some of you who have studied matrices in your 11th grade or 12th grade will easily understand this notation, right? So typically what I write is I write A 1 cross n. As soon as I see this, I know that my vector A actually has one row and n columns, right? When a vector has only one row, it's called a row vector. Similarly, for a column vector, suppose if I have a vector B, and if I have components B1, B2, so on, so forth, Bn, right? Now it has n rows, first row, second row, so on, so forth, n rows, but it has only one column. So I'll represent this as n cross 1. Here n represents the number of rows again, and 1 represents the number of columns. So if I write a vector like a column, I can write, given a vector, right, given an array, I can write it either as a row vector or a column vector, right? We'll see how these are useful. I'm just explaining you some notation here and how to. So if somebody says b n cross 1, I immediately understand that this is a column vector because it has n rows and only one column, right? Again, just extending this idea, matrices are typically represented as a m cross n. So if I have a matrix here with m rows, 1, 2, so on, so forth, m rows, and if I have n columns, 1, 2, 3, so on, so forth, 10 columns, this is called a matrix of size m cross n. You can think of matrices as double array, as basically an array of arrays, right? Double array of arrays. For those of you who are from computer science background. Those of you who are from other backgrounds, you might have come across what a matrix is in your high school or even in your undergrad first year. It's a very, very simple and straightforward concept. So what you represent here as a subscript basically tells you how many rows and how many columns exist.